This video covers our motivation, the discrete question itself, the key definitions, and the flagship splice collision. We will present the evidence through exhaustive sweeps and our rigidity theorem, followed by how our work positions itself within the field and some open questions for future collaboration. The motivation stems from the failure of the continuous Jacobian conjecture in July 2026. It was claimed that a polynomial map with an everywhere invertible differential must be globally invertible. However, Alpagay provided a counterexample, showing that local invertibility does not force global injectivity in the continuous setting. This leads us to the discrete question: can the same failure occur in graph rewriting? We investigate this within a Wolfram model-style, DPO graph rewriting framework. While local invertibility is clear, we ask if this induces global injectivity on isomorphism classes. Our answer is yes. Collisions exist, even for census-preserving rules. To understand this, we need a few definitions. Semantic D1 ensures local invertibility. History ambiguity arises when the result admits a reverse match that yields a non-isomorphic predecessor. A collision occurs when two distinct states evolve to the same class. Census-preserving rules are those that maintain the same number of vertices and edges. Our flagship example is the splice collision. The rule splices a loop into an edge. We identify two non-isomorphic states, S1 and S2, which both evolve into the same directed forepath. Because the image forgets the original location of the loop, this provides a certificate of the failure of injectivity. This diagram illustrates the splice collision clearly. Both the outstar and instar configurations evolve into the same directed forepath. The identity of the loop vertex is essentially forgotten during the rewrite, a phenomenon we describe as discrete monodromy. Our experimental sweep provides evidence for these findings. Out of hundreds of rules enumerated, we identified many collisions. Importantly, every collider found exhibited history ambiguity. At the smallest scale, the only rule that remained history unambiguous did not collide, demonstrating its rigidity. This observation led to our rigidity theorem. It states that a semantically locally invertible rule that is also history unambiguous has injective one-step evolution on isomorphism classes, regardless of the updating policy. This provides the theoretical counterpart to our empirical findings. Our work is complementary to research on space-time reversible graph rewriting. While others provide conditions to design reversible systems, our certificates show that dropping certain constraints can lead to genuine global collisions. It is a collaborative effort to map out these boundaries. Looking ahead, several open questions remain. We are interested in the relation between surjectivity and pre-injectivity in dynamic topology systems, the potential dichotomy between ambiguity and collision, and how these classical findings might translate into quantum regimes. In summary, local invertibility does not imply global injectivity. The splice collision serves as a minimal, verified certificate. History ambiguity is a necessary condition for these collisions, and our rigidity theorem confirms the behavior for unambiguous cases, providing clarity on the limits of these rewrite systems.